Hello everyone, I'm Shulin from Peking University. Today I'd like to present our paper, Generating Efficient Solvers from Constraint Models. Combinatorial problems exist in various domains. Typical CPs include register allocation, combinatorial auction winner determination, DNA mapping, and so on. A CP usually consists of input arguments, variables, relations, and 0 or 1 objective function. To solve such a problem, we need to find an assignment of variables such that all relations are satisfied and the output of the objective function is optimized. For instance, 01 knapsack is a classical CP. There are n items and a knapsack of capacity C. Each item has its own value and weight. We're supposed to find a subset of items such that the weight sum is at most C while the value sum is maximal. In this problem, there are 4 input arguments n, c, and items value and weight. 1 variable, a subset of items. 1 relation, the total weight is at most c, and 1 objective function that maximizes the total value. People usually use constraint solvers to automatically solve CPs. A major limitation of existing solvers is a scalability issue. Additionally, the state-of-the-art constraint solvers have overly complex architectures. Therefore, configuring or tuning requires a great deal of expertise and demands lots of fine-tuning effort. To overcome the scalability issue of constraint solving, researchers propose different optimization methods. However, the optimizers make solvers more complex and introduce more overheads. Some previous work also proposed solver generators to automate tuning. However, the tuning process can be ineffective and inaccurate, making the generated solvers inefficient. To write the code for solving a CP, one should formally model the problem first, then characterize the problem properties, design and optimize a solving algorithm based on the properties, and finally implement the corresponding code. There are 2 major challenges in automating solver generation. First, give a CP, how can we characterize the problem properties? Second, how can we decide which search strategy to adopt and which optimizations to apply based on the properties? To address these challenges, we define 4 problem properties: the search space, value ranges of subfunctions, the monotonicity of objective function, and overlapping subproblems. Prob 1 determines the complex of a brute force search algorithm and is used to design the basic strategy. Prob 2 and 3 define the feasibility and optimality of search branches and are used to prune unpromising branches as early as possible. Prob 4 is one of main properties that suggests that the given problem can be solved via dynamic programming. We use Prob 4 to design whether to apply DP optimization. In this paper, we design and develop a SoGen solver generator, SoGen. To solve such a CP with SoGen, users need to model the problem using a constraint modeling language, PDL, and send the model to the generation engine. The engine will automatically characterize the problem properties, then design an algorithm and generate the corresponding solver. Such a problem-specific solver can take any problem instance as input and return the solution correctly and efficiently. Given a PDL model, the SoGen's engine first analyzes the model to build an identify table, then decides the independent variables and generates a basic search algorithm. The algorithm will be optimized by branch pruning or dynamic programming if possible. Finally, the engine implements the code according to the algorithm and returns it back to the user. Step 1 to 4 automate algorithm synthesis, and Step 5 automates algorithm implementation. The first step is to extract the identifiers from the PDR model and reduce the specified value ranges of variables in order to shrink the search space. The second step is to find the minimum independent variable set among all variables. To decide which search strategy to adopt, we characterize prop1 by the independent variables found in step 2. If prop1 corresponds to few independent variables, SoGen generates an iteration-based algorithm. Otherwise, SoGen generates a recursion-based algorithm. In step 4, SoGen optimizes the basic algorithm based on prop2 to 4. SoGen is capable of applying two types of optimizations, branch pruning and dynamic programming. There are two types of pruning, feasibility-based and optimality-based pruning. If prop2 value ranges of subfunctions is not empty, SoGen applies feasibility-based pruning. For example, in 01 knapsack, since any intermediate weight sum should never exceed the capacity, a branch can be safely pruned once the weight sum is larger than C. If prop3 the monotonicity of objective function holds, SoGen applies optimality-based pruning. In 01 knapsack, if the potential upper bound of value sum is not greater than the best result found before, the branch should be pruned. SoGen also automates dynamic programming when prop4 overlapping subproblems holds. In 01 knapsack, prop4 holds because the number of subproblems is far less than the size of the search space. Then SoGen conducts DP in top-down manner and calculates the optimal solution effectively. It's worth mentioning that SoGen is the first tool that aims to automate DP implementation from a general constraint model. Finally, SoGen implements the design algorithm based on the following 6 predefined templates and returns the code of the solver program. We apply SoGen and other 2 general solvers to 9 classical CPs. For each problem, we defined 5 instances with different program size, executes each tool on each instance 3 times, and reported the average time and memory costs. We also compared SoGen with another solver generator, Dominion, on 3 CPs in the second experiment. The settings are similar to the first one. The results show that SoGen solver work better than 2 general solvers by handling more tasks given limited time. SoGen solver accelerated the solving process by up to 3 to 4 orders of magnitude. We also observed that SoGen outperformed Dominion by generating solvers with lower runtime overheads. Its solvers can also resolve more constraints by using less solving time and memory. In this paper, we present SoGen, a novel approach of generating efficient solvers. SoGen automates static property characterization, basic algorithm synthesis, branch pruning, and dynamic programming optimizations, and code implementation. SoGen is unique because it statically reasons about 4 problem properties, automates the decision-making process to adopt distinct optimization strategies based on the problem properties, and automatically designs dynamic programming. That's all. Thank you. Any questions?